Hello and welcome to another video. In this video we're going to be doing the second problem from the weekly contest 382, which is find the maximum number of elements in a subset. The first one was like super easy, so we're going to do this one. This one's kind of good. So you're given an array of positive integers nums, and you want to select the subset of nums which satisfies the following condition. So essentially you need some kind of subset that every number is the square of the previous number and then it goes back down. So it's kind of like a triangle shape, where every number going up is the square of the previous number, and then every number going down is the square root. So basically, just for an example, so you'd have to have like 2, 2, 4, 4, and 16. So going up, it's all the square, and then going down, it's all the square root, and the left and the right side are the same length. So the middle number has to be like the biggest one, and so on. And so they show you like what satisfies things and what does not. So 2, 4, 8 does not, because it should be 2, 4, 16. So let's look at the examples. So in 5, 4, 1, 1, 2, 2, you can pick any numbers you want, and you're just asked to get the longest subset. So the longest subset is 4 to 2, and you can basically like move these numbers around. So 4 to 2 can make 2, 4, 2, which is a length 3 subset, and that's the longest. And for 1, 2, 3, 4, there are no squares except for 2 and 4, but you need 2 of each. So you can only use one number. So your subset can just be like 1 or 2 or 3 or 4. So this problem is very similar to another problem where you are asked to find, you're given an array of numbers and you're asked to find like the longest sequence where every number is one number or one number apart. So essentially you're given some array and then you're asked to find the longest sequence where every number has to be exactly one number apart. So a sequence could be like 2, 3, 4, 5. It's basically that, just a little bit harder to see. So essentially, in order to make a valid sequence, we have to have some number with a count of at least 1, right? So let's say this number is x. And then you have to have to the left and to the right square root of x, the square root of x, and then square root of this, right? So square root of x, square root of x, and so on and so on and so on. So the way to do this without actually doing repeated work, because you need an O of n or n log n or something solution, is let's just think about what valid numbers we can use for the top and when would we ever use it. So for this like triangle, we want to use numbers that, like, let's just think about it, right? Like let's say we have a value x and we have 2 of them. And we also have a value y that's x squared. If we have that, then we're never going to want to use x as the top, because for whatever pyramid you could build with x, like if there's a valid pyramid with x, so let's say you have like a, b, x, b, a, well, we can just, since we have 2 x's, we can just make this pyramid bigger, right, and put in a y here. So we can write this down. So we never use a value as the top of the pyramid when that value squared exists and we have 2 of our current value. So we need to have 2 of our current value, right? Because let's say this whole thing is true. Like let's say we did have this y that was x squared, but you didn't have 2 x's. Well, then you can't just like put y at the top because you need 2 x's for that to work. So you just need to basically make sure that you have 2 x's and then this will work. So essentially, let's kind of walk through, let's maybe make some numbers and let's like do something and see how this will work. So, and I'll show you, and I'll show you why this will be a linear time. So let's just have some numbers here. The index doesn't matter at all. So let's just say we have like 2, 4, 2, 4, 2, 4, 16, 16, 64, and like a 2 or something. So I think this shouldn't be 64 actually, so I'm not sure off the top of my head what 16 squared is, but we'll just say it's 16 squared. And then we'll have another 2. So the first thing you're going to want to do is you're going to want to go through this and get the counts of every number. So if we take a look, we have 3 2's, we have 4 2's, so we have 4 2's. Then we have 3 4's, and you can just use a basic counter in Python. We have 2 16's, and we have 1 16 squared. So now we can go through all of our keys and basically figure out, like, is this a valid top value based on our principles? If it is a valid top value, we'll just go down all of the numbers in our keys that we can have, and then we'll figure out, like, what's the biggest triangle thing we can make, like this shape, and then what's going to be the length of it. And for every single valid top, we will do that. So let's go through this. So for 2, to consider 2 as the valid top of the pyramid, we're going to say, okay, is the count of 2 or more? Yes, it is. And does 2 squared exist? Yes, it is. So 4 exists, and we have 2 2s. 2 will never be like the top of the best pyramid we can make, because we can always just do this, right? Whatever 2 can make, we can always just do this, and then have the pyramid under the 2s over here and over here, right? So if 2 can make like A, B, 2, B, A, we can just put those BAs here, right? So we can just put it like this. And that will just be bigger. So 2's never going to be a valid top of the pyramid. So let's try another value. You can just go down the keys in order, and then basically you're only going to traverse each number one time, because you're just going to check, is it a valid top? And if it's not a valid top, you're just going to skip it. So when you're actually building the pyramids, you will only include each number once in a pyramid. So now for 4, we're going to check, okay, for 4, is there 4 squared? Yes, there is. And do we have multiple 4s? Yes, we do. So 4 is never going to be a good candidate as well. Then for 16, we're going to check, that's going to be our next key. Do we have 2 of them? Yes, we do. And does 16 squared exist? Yes. So 16 will never be a valid top. And then finally for 16 squared, we're going to check, do we have 2 of them? No. So if we don't have 2 of them, we don't have to check if this thing squared exists, because even if it does, in order to have this thing, right, so the 16 squared, in order to have this be the valid top, you need to have 2 16 squareds. And because you don't, then 16 squared will be a valid top, like it might be a possible solution. So for 16 squared, we're going to say, okay, let's just put 16 squared at the top, and let's just traverse down all of the values until we no longer get to a number that we have 2 of or it doesn't exist. So this is going to be 1. This is going to be like one value. So we're going to say, okay, does 16 exist? Yes, it does. We have 2 of them. So that's fine. So essentially we're going to say, okay, that's fine. So our initial count is going to be 1 for this top. Then because 16 exists, we have 2 of them. So we will add 2 of them. And so I'm just going to draw this, but I'm not actually going to make the structure in the code. I'm just going to traverse down the actual roots. So we're going to have 16. We're going to have 2 of them. Then we're going to check, is the root of 16 available? And do we have 2 or more of those? And we do. So we have 4. So we do have 2 more of those. So we'll add 2 more to our pyramid. Then we're going to check, is the root of 4 available? And do we have 2 more of those? Yes, we do. So this is going to be 2 and 2. So we'll add 2 more. And then we're going to check, is the root of 2 available? And do we have 2 of those? No, the root of 2 is not available. So we're done. So we traverse down 3 different children, and each one of those children is going to appear twice. So you're going to have 2 times each child plus the actual root top of the pyramid. So that'll be 7. And that's going to be your answer. And so notice that the only traversal we actually did is this path, right? 16 squared to 16 to 4 to 2. We never actually traversed down any of these that weren't a valid top. That's why this is going to be order n, because you will never traverse down like the same node. You're never going to traverse down a path that has like this node, for example, multiple times. At least I don't think you will. There might be a case for that, but I don't think you will. Or even if you do, it'll be super rare. But I don't think you will. Because in order for there to be a valid path with this, if this was a valid path, then the only way to have another path with the 16 is to have some other value up here. And if some other value was up here, then you would have to have 2 16 squared, so then this just wouldn't be the top. So I think I am right where you are only going to traverse down each value once. That's kind of the idea. So let's actually go through like this 1, 2, 3, 4 example really quick as well. Yeah, actually I think we can go through these other 2 really quick as well, because these are pretty fast. So for 5, 4, 1, 2, 2, so we're going to have 1 with a value of 1, 5 with a value of 1, 4 with a value of 1, and 2 with a value of 2. So let's kind of go through this. So for 1, do we have 1? Oh, I forgot one more thing. So for 1, there's also like a unique case. For every other value, the square root and the squared value is going to change it. But for 1, the square root of 1 is 1. and 1 squared is 1. So 1 is a unique case. So actually, if you have like, let's say you have 10 ones, you can actually make a pyramid like this, where it'll be like 1, 1, 1, 1, 1, 1, 1, 1, 1, by using 9 of them, right? So 1 is basically a unique case where you have to figure out how many ones you have, and then you can use however many ones you have, you can use the biggest odd number you have. Because essentially you can make this endless pyramid of ones where it just keeps going, but the pyramid has to have an odd count, right? It has to have 2 of each child and then 1 top. So essentially whenever you have some count of ones, let's say we have 10, we just take the biggest odd number closest to 10. So in this case it'll be 9. So that is something I forgot. So yeah, so we can check that separately. Okay, so now let's do the rest of it. So for 1, we're just going to check how many ones do we have, and we only have 1. So let's just write our result as 1 for now. Then we're going to go to 5, and we're going to say, okay, do we have 5 squared? No, we don't. So then we'll try a pyramid with 5 at the top. Do we have anything with square root of 5? No, we don't. So then this pyramid is only going to be length 1, which we already have. Then for 4, do we have 4 squared? No, we don't, and we don't have 4 2s. So let's try, or we don't have 2 4s. So let's try using 4 at the top. So if we have 4 at the top, do we have square root of 4? Yes, we do. Do we have 2 of them? Yes, we do. So we can build this, and this will be 3 nodes. So our answer here is 3. And for this, because every value is unique, you will basically never have, you'll never be able to build any pyramid, so that's why it'll be 1. So you could do this with accounts as well. But yeah, that's the other thing I forgot, is it's kind of hard to figure out as well. Without, what ended up happening was I ran this, and then I noticed this edge case where the array just had like 10 9s or something, and I was getting the wrong answer. Or 10 1s. But yeah, that's basically it. So like I said, it's kind of similar to the other problem where you're asked to get the longest consecutive streak. The way to make sure you don't recompute these pyramids is you just always check, is this a valid top? And for it to be a valid top, that means the square of this number can't exist. And if the square of this number does exist and you have more than 1, then you're just better off picking the bigger number. And that's how we avoid the repeated work. So let's take a look at the code. And here it is, pretty easy. So first you just get a count of every single number. And then like I said, 1 has a unique case. You can write outside. So essentially 1, you basically need to take the closest odd number to whatever you have. And this is basically doing this, right? So it's just basically saying, let's get the number of 1s if it's odd. And if it's not, let's subtract 1. So if it's like 10, we'll use 9. If it's 1, we'll use if it's 2, we'll use 1, and so on. Because to build a pyramid, you have to have an odd number of numbers. So for 1, we do separately, and then for everything else is all the same. So you just check if for every single key, does a squared key exist? And if the squared key exists and you have more than 1 of the key, that means this key will never be like the best solution. So we don't even have to build a pyramid with that. We can just skip until we get to the good key. Then, once we get to a valid like top of the pyramid, we are going to say our count is 1, and we will just basically keep trying to square root our key and keep checking, does that square root exist, and do we have 2 of them? If we do, let's add 2 more to our current count, and let's keep taking the square root until we run out of square roots. Then finally, we get a count of this whole pyramid that we made, and just maximize our result. So, pretty easy. Yeah, and I think like this, so I think the really good runtime is like 750, so all the runtimes are really close to each other. So usually what happens is if I run it like a few times, like it'll be in like the top 100. So it doesn't really show yet, but yeah. So I can actually look at my submissions if I go back. So you can see like all these submissions are around the same, and if I look at like this one, let's say, then this beats 100%. So all the submissions are like very, very close to the same runtime. Just kind of depends on like, this isn't very consistent. So yeah, like this is 750, or this is 760 that beats 100%. This is 770 that beats 25%. They're basically the same runtime. Okay, so yeah, so here the time is going to be O of n, because like I said, we're only checking, like we're only going down the pyramid 1 time for each number. We're eliminating invalid pyramids right away, and then the space is O of n because we have this counter. So kind of it for this one. Definitely think this was kind of an interesting one, not super easy, so let me know what you think about this one. If you have any questions, as always, write in the comments. And I'm going to do the third problem relatively shortly, because I think it's actually the easiest third problem I've ever seen in a contest. So I'll do that right after this one, and then I'll do the fourth one a little bit later, because it looks like it's an 8-point problem, so that one might take me a while. We'll see how that goes. But yeah, thanks for watching, and I'll see you in the next one.